So let's consider this young lady who's going to go down into the water, and think about what's the force that's going to be on that faceplate that she has there. Okay, so we've set up a certain area, and I just kind of made that up, of course, and I made up the depth, of course, but we're gonna, it'll be instructive to get some idea. 30 meters doesn't necessarily sound like a lot. That's not very far. I mean, we're talking about 99, 100-ish feet, something like that. Okay, and but underneath the water, that's a long ways. Okay, and in the world of scuba, my understanding is 60 feet is generally seen as the greatest depth most people go to. If you go below 60, they consider that a deep water dive, and so 100 feet under the water with scuba gear would be that would be considered pretty deep. All right, so just for some reference there. So if she's going to go 30 meters down, and we want to find the force on her, okay, when we say the hydrostatic force, specifically what we're talking about is, let's say here's her little face plate here, and comes back, and her head's in here, back in here like this. So when we specifically talk about the force, hydrostatic force here, we're talking about what's the force from the water onto her plate. Okay, just like that. Now, so in order to do that, we're going to need the pressure, and we're going to need the area. Of course, we've got the area that's given to us there in the question itself. We just have to find the pressure. Okay, and so what we'll do then is we're going to need this equation down here to get the pressure. Okay, so let's take a look at that. And so I need to change pen colors real quick. Oops. All right, so make this just a little bit bigger. So the pressure down there where she is going to be the ambient pressure plus rho g delta z. Okay, and really all we have to do is plug in numbers into this thing. Okay, and so we know all of those numbers, and I'm going to do it with some units, something I'm going to start doing from here on, in order to sort of help you see how the units work into some of these things. So the ambient pressure, we're going to say, is 101,000. Okay, and that's newtons per meter, like this. And then plus, we have 1,000 kilograms per meter cubed. And that's going to be times g, which is 9.81 meters per second squared. And our z is 30 meters. Okay, now the z here assumes that it's down from the surface, so we don't need to put like negative 30 or anything like that. We can just slap the 30 in there and go with that. Okay, now when you add all those things up, okay, what you're going to end up getting is, with 3 sig figs, you're going to get 294,000. Okay, now let's figure out what's going on with our units. Okay, because the units are actually newtons per meter squared. There's a square on there. Okay, so if we have a kilogram meter per second squared, that's a newton. And you can see a meter here loses this, so we're going to be left with newtons per meter squared on that thing. Okay, and that's really the same thing as a Pascal. Okay, and so we could write this as 294 kilopascals. Okay, now it's sometimes useful to figure out what that is in terms of ambient pressure. Okay, so we might want to come in here and say, well, how many atmospheres is that? Well, if we divide this thing by 101 kilopascals, okay, what we're going to end up getting is 2.91 atmospheres of pressure. Okay, so one of the weird things about pressure is we've got a lot of different ways we can talk about the units. Okay, so we can do newtons per meter squared, we could do pascals, kilopascals, atmospheres, and there are others. Okay, there are others. And then since there are 14.7 psi in one atmosphere, we could also convert that to psi, which would be 42.8 psi. Okay, something like that. All right. The rule of thumb is every 10 meters of depth is basically another atmosphere of pressure. All right. So at the very top, your total pressure is just ambient, just the atmosphere. You go down 10 meters, you've added another atmosphere. Go down 10 more meters to 20, you've added another atmosphere. Go down to 30, you've added another atmosphere. So you're talking about basically 3 atmospheres of pressure. And you can see that's what we got here. Okay, just like this. Uh-oh, except I screwed up my number. Shoot. Okay, let me fix this. In the number I gave you, I didn't add that to it. It's just the gauge pressure. It's just the gauge pressure. Okay, sorry about that. So that's why we've added basically 3 atmospheres of pressure there. That's not the absolute pressure. If we wanted the absolute pressure, we'd have to take our number here and we would add to it the 101, so we'd get 395. Like that. That would be the absolute pressure at that depth. Okay. But a lot of times we're not too worried about that. So when we say the hydrostatic pressure, you do have to be a little careful with your context. Are you talking about just the gauge pressure, or are you talking about the absolute pressure? Okay. Usually you're talking about the gauge pressure. All right. And so the reason for that is because inside here where she is also gauge pressure. So what really makes a difference on one side or the other is on the inside we've got atmospheric pressure, on the outside we've got atmospheric pressure plus the gauge pressure due to the depth, like this. Okay, and so the atmospheric pressure on the outside and on the inside, their efforts on the face mask cancel each other out. So all that really matters is the difference. Remember when I did this or this? Okay, so all that really matters is the difference. And so what we found there is the pressure, the gauge pressure, 294. All right. Now, to turn that into a force, we got to multiply it times the area. Okay. And so what we want to do, since we have so many different units for pressure, we want to pick ones that are going to play nice. Okay. So in other words, we don't want to plug in PSI because our area is in meters. We don't want to plug in atmosphere. We don't want to plug in millimeters of mercury or any of the other crazy things that we could talk about. Instead, we just want to go with the newtons per meter squared number. Okay. So we're going to have 29,400 newtons per meter squared. And then we're going to multiply that by 0.15 meters squared. Okay. And you can see my meter squared terms are going to go away. And so we're going to be left with 44,145 newtons. Okay. That's a lot of force. Okay. That's a lot of force. In fact, it's so much force when I calculated that, I was like, what? What does that even mean? That number is so huge. And so I was like, okay, well, that's approximately the same force as the weight of a mass that was about 4,500 kilograms. Okay, just like that. Okay, so I'm like, that's something I can get my head around. On the other hand, we could say, well, what if we converted newtons into pounds? Okay, and if you do that, what you end up getting is that this is pretty close to 10,000 pounds. All right. And we're going to work a problem involving my Toyota Sienna van. And it's just under 5,000 pounds. So this would be like having two vans, two vans on your face. Okay. Which is, it's pretty ridiculous. It's so ridiculous. I'm gonna have to go back and verify my numbers here at the end of this video. Okay. Now, that does, however, also explain a couple of things. So if you've ever been, I used to like to, whenever I was in a pool, if I jump off the diving board, I always like to go to the bottom and just kind of, just sort of hover in the water. And it's just like it's peaceful and your body's almost weightless. And I don't know, I find it very relaxing. I always like doing that. But you feel that on your ears, right? You feel that on your ears. You get under that water. And so there's that pressure is there. And when you're underneath the water, if you take a super deep breath before you go down, even when you get down, you begin to feel like you don't have enough air in your lungs. And it takes a little while to get used to that feeling, and then you can just hang out. But until you get used to that, you feel like you get down there, you got to take a breath because it feels like your lungs are empty. Okay. So the problem with this sort of deep sea diving device is that their chests are exposed. Okay. And you're going to have to provide pressure in the helmet, enough pressure to push back so that the people can actually take a breath. Okay. Because all that pressure isn't just on the face mask, it's on your chest cavity, and it's going to squeeze you like this. So your little friend on the surface is going, right? But you can't breathe. All right. The force on your chest is so great that you can't breathe. So the person on the shore is going to have to provide basically have to provide as much pressure as what we just calculated in order for them to be able to breathe. And that is not realistic to expect one person to be able to pump like that for that amount of time with that effort. So the risk of drowning here is quite significant. And I hope all those 4 intrepid people were safe. Okay. All right. So there we go. Now our next example we're going to look at actually involves my van and the tires.